So if you all hear me, I'm going to start now. So yeah, it's good to see so many of you here. Uh, I guess like previous days, um, if you have any questions, you can pop it on the chat or just yeah, just raise your hand, and either me or Juan will be here to answer your questions. So yeah, um, right. So today's session is going to be on linear algebra for C++. So it's slightly different from the other lectures that you've had before because it's not strictly part of the C++ standard, but it's still very useful. And so it will be, I guess, slightly less abstract. It'll be a bit more applied. And in fact, it feels like in C++, this functionality is sort of missing as any good scientific computing language, you would expect there to be good linear algebra support. So I'll mention a little bit later where C++ plan is in terms of having linear algebra as part of the standard. But if you're coming from Fortran or if you're using Python, you will have NumPy, and in Fortran it's very fundamental, it's sort of baked into the language. So yeah, we'll see what how we can get around doing so. Um, so obviously, linear algebra is a very wide subject. There's a lot of mathematics and the basics of it. I won't be assuming too much. There's also a lot of detail in terms of implementation and optimization. It's a very big subject, very useful. So if you want to read more about it, there's lots of resources. But today we'll be focusing on just using the eigen library, which is, I guess, one of the easiest to use and very comprehensive one that you can use for your applications. Okay, so the course was based on a previous course that was given by Chris and Rupert. So yeah, right. So this is what we'll be going through today. So I'll be going through sort of why we need a linear algebra library and what we expect to have in such a library. And I'll go through eigen3 in a little detail, sort of talking about the functionalities it have. So what you can do in terms of matrices and solvers, and give you some general recommendations. And I'll go through a demo at the end to solve a 1D diffusion equation uh, exercise. So, okay, so linear algebra, what do we need it for? So the most basic form of linear algebra is just manipulating vectors and matrices or solving linear equations. And it's useful for all sorts of scientific computing. One example is solving PDEs, partial differential equations, but any form of simulations in all sorts of applications in finance, graphics, machine learning, at the most basic level, most of the computation is just linear algebra computations. So what do we expect in terms of a library that supports linear algebra? First of all, we would want it to be able to represent different objects, like vectors and matrices. So vectors are very simple, but matrices have a bit more intricacies. So for example, you can have dense matrices, which is just your basic matrix storing every value, but you can also store them as sparse matrices. These are useful for when your matrix is very large and has a lot of zeros in them. This occurs a lot in differential equations or very big physical systems. I will go through a little bit more detail later, but then there are also special matrices like diagonal symmetric matrices, and how you store them also it gives you different benefits. There are also operations that you want to do between them. So the most basic ones, if you want to be able to multiply matrices, you want to be able to transpose them, and also if you treat them as geometric transformations, you want to be able to rotate them, you want to be able to do various sort of transformations. And another big topic is about solvers. So these are to help us solve various linear systems. For example, if you have here we have ax equals b. So A is a known matrix and B is a known vector, and you want to solve for the solution in X, or you want to obtain the eigenvalues or the singular values of a certain matrix. So these are very important in different sort of physical simulations. There are different techniques that can help us achieve these calculations. So for example, there are these factorization like LU and QR factorizations, or there are also indirect solvers. So especially if you have a very big matrix, then it's impractical to solve it directly in terms of, say, finding the inverse. It would be much better to approximate your solution and get iteratively closer to it. So these are called indirect solvers, like conjugate gradient and different variants of it. So, okay, so other than being able to represent and manipulate different objects, you want also to be able to represent different numeric types, because very often in scientific computing, we don't just talk about floating point numbers or integers. We also want complex numbers, or you want to define your own more complex data type as well. So next, okay, so why would you want to use a linear algebra library as opposed to writing your own vectors and matrices yourself? So I remember back when I was coding for my physics simulations, I used to just write a SCD vector and manipulate between them. When I multiply matrices, I just go through every element. Now, in hindsight, it's a very dumb way to do it because there are much easier ways to do it through a library, much cleaner, much simpler, and also more performance. So definitely faster than what I could have written or what I wrote myself, and it's probably more correct than what I've implemented myself as well. And it's more expressive. So if I want to change, say, the data type that I want to use, it'll be much easier because under the hood, it's all just templates, as you've touched on before. So these libraries are very useful. So yeah, so if you're going to use linear algebra, I would recommend you to not reinvent the wheel. Don't write it yourself. Just use one of the very good libraries out there for your linear algebra needs. So there are, for different applications, there are different good libraries that you would want to use in for C++. So the one that we're going through today is Eigen. It's very simple. It's very small and very lightweight. Then if you want bigger problems, for example, that you will need to parallelize with MPI, or you want more complicated, more sophisticated solvers, especially distributed ones, then you will want to use a bigger library like PETSI, but that will come with more complications in terms of setting up. But yeah, if your simulation or your code is very big, it is not a bad idea to use one of these libraries. It's particularly good for solving PDEs, say in fluid simulations. Yeah, but there are also a lot of other optimized libraries. So LAPACK, which is linear algebra library. So there's a lot of routines that are specified that you can use, and they tend to be optimized for different architecture as well. So for example, on the GPU, your vendor would give you a set of libraries for optimized routines, say, so BLAS is sort of basic linear algebra, and you can have also different routines that are optimized for that particular architecture on GPU and CPU. So here are just some examples that I've listed, and OpenBLAS is an open source one, which is very performant as well for basic linear algebra routines. So the punchline is just that for your purpose, there are very simple implementations that you can use like Eigen, but if you really need to optimize for a particular implementation, you would want to dig a bit deeper into what libraries are provided for where you're performing calculations. So as I mentioned, it's not currently part of the C++ standard, but there are plans, or there's a draft to include it as part of the C++26 standard library. So this will include linear algebra operations, as well as, I think, ND arrays, so multidimensional arrays or tensors will also be supported. So this is still a plan, but if this does go through, it'll be very nice, just like the standard algorithms that you have looked at before. So yeah, and just like if you come from another language like Python, you will know the benefits of having a unified or a standard library approach like NumPy, where we can just expect it to work and everyone can just learn that, and that's it. But I've included some links here in case you want to look at different libraries and different capabilities of them and see which one you want to use for your applications. Okay, so eigen, as I mentioned, it's very simple to use. One of the benefits is that it's a header-only library. So that means you don't need to compile it. You only need to have the header files, which you can download from this link, or you can do apt-get to get it. And on Archer, which is where you have been running your codes, you can just do module load eigen. Yeah, I'll just put in the chat so that if you want to try it yourself, module load eigen, then you have access to the library. But then if you don't have it, you can just download it and put it in your include path, and when you compile it, then everything will be ready. So it other than being very simple to use, it also contains optimization for different processors. So it has some vectorized routines. So it is already optimized. So you can expect good performance from it already. So in terms of the capabilities it has support for dense and sparse matrices, vectors, and arrays. So arrays are like vectors, but they are more suited for operations that are coefficient-wise operated. And we'll have some examples later. And in terms of solvers, it has supports for some of them. It's not the most comprehensive, but it's probably good enough for most applications that you need to use. Okay, so let's get started with some of the most fundamental feature of eigen is if we want to have a matrix. So say if I want a dense matrix, which is what you would naively store a matrix as is a dense matrix where you store every element. So what you need to do is just include the header file in eigendense. Then you have access to all the templates. So here I'm trying to declare a 10 by 10 matrix of double. So this is what you do. So you specify the size and the data type, and you can operate on them. Say you can set the value, set 0, or you can set the value 1 by 1, and then you can print them out. So this is not that different from a normal 2D array that you can have. So the size is fixed. Once you've declared this, you can't change the size. So if you do want to change the size, eigen has a different kind of size parameter called eigendynamic. So in this case, if I put dynamic instead of a set size, you can resize it afterwards. So here in this example, I first set it to 64, 65, and I resize it. So this is not that dissimilar to SED vector, where you can resize it afterwards. But then here you can have a 2D matrix version of that. Yeah, if I'm going too fast, just say it on the chat and we can slow down a little bit. So eigen also provides a lot of these basically aliases where you can declare these matrices very easily, because if you imagine typing this it gets quite tedious quite quickly. So it has predefined some type defs for you. So for example, I can have a matrix 3D, which is a 3 by 3 double matrix, 3i, which are int matrices, and you can have, say, dynamic size. So matrix XD is exactly what I'm declaring here. So you can also define your own ones, but pre-built, there are already a lot of very good ones that you can use. So it's also easier to understand what your code is doing. Right, so once we have the matrices or vectors, we can operate between them. So what kind of operations can you do? So the most basic kinds is I have two matrices that are of the compatible size. So I have a 5 by 10 and a 10 by 2. So these two matrices can be multiplied. So you have an overload operator, so you can just multiply matrices and exactly as you expect, and same for a vector. And other operations you can do like dot product, cross products, transpose. These are all available, and you can also set values with these functions. Now, everything is very straightforward. Another thing that's very useful is these arrays. So if I have an array what arrays are good for is I want to operate on every element. So here in this example, I have an array, and then I can call a sign function for each of the elements. So these are the kind of operations where arrays are useful for. But then just a little warning that arrays are not like vectors, so you can't operate between matrices and arrays. Yeah, so it's just they're not vectors, they're just something different. So another useful thing that eigen lets you do is say if I've declared if I've allocated the memory for a vector, then I can sort of overlay that memory with a view as an eigenmatrix. So here I have allocated 1,000 elements doubles in a vector, and I want to view it as a 100 by 10 matrix. So what I do is I use an eigenmap to map the data, this A, into an eigenmatrix. So now I've turned this A into a 100 by 10 matrix. So I can just allocate elements as I would with a normal matrix, and it doesn't take up any additional memory. It will just be a view on top of the memory that's already been allocated. And if I want to give another view to it, say I now want to view it as a 10 by 100 matrix instead, I can do so as well without doing any copying to the underlying memory. So it just gives you access, different access patterns of your pre-allocated memory. Right, so what I've been describing are all dense matrices, but what about sparse matrices? So as I mentioned, sparse matrices are matrices that have a lot of zeros. There isn't a very strict definition of when a matrix becomes a sparse matrix. But then in some applications, say you're trying to discretize a finite difference operator or differential operator in a large systems, then you end up with a matrix, for example, with elements just along the diagonal with maybe one or two elements next to it. Then as your system grows big, you can easily have a matrix with just 1% of the elements that are filled. So then it will be very useful, or sometimes even necessary, to store them as a sparse matrix, because if you store all the zeros, your memory will just blow up, and it'll be impossible to store them, and also very inefficient to operate between them because you're just striding through many zeros. So behind the scene, there are different methods of storing sparse matrices. The way that eigen stores them, it's a modified CRS, which is compressed row storage. So basically, you just concatenate all the rows to with elements and store them, but it doesn't exactly do a CRS. So what it does is it adds a few zeros in between so that you can easily add elements to it. So yeah, if you're interested, there you can read the documentation and see why they do it this way. So yeah, so if you want to use sparse matrices like before, rather than including the eigendense, now you include the eigensparse header. You can see it's very easy to declare a sparse matrix. So here I've declared a 1,000 by 2,000 sparse matrix, but you can also have column major or row major, basically which order you store them in. And you can also call a vector. So this is how you declare that you want a sparse matrix. Obviously, what is actually stored inside or how big this object is depends on what goes in it. So the next thing we'll talk about is how do you fill a sparse matrix after you've constructed one. So as I said, what you store in a sparse matrix is basically just the non-zero elements. So what you need is the non-zero elements and where they are, so the sort of coordinates of the element. So the easiest way to do this is to create a list of triplets. So a triplet is just 3 numbers. so containing the location, so it's I and j, and then the value, or the element. So you create such a vector. So here I have vector triplet list, and then you use this m dot set from triplets. So set from triplets, basically you provide it with a triplet of coordinates and elements, and it will build your sparse matrix in one go. So in this very simple example, you can see how you would construct a sparse matrix from scratch. And this will be useful in one of the in the exercise that we look at later on. So what can we do once we have built such sparse matrices? So most of the operations that you can do as for a dense matrix, you can also do the sparse matrix. So like transpose and adjoint, you can add them, you can multiply them, but you can also operate between sparse and dense matrices. So for example, you can add a dense matrix and a sparse matrix to get another dense matrix, or you can multiply a sparse and a dense matrix. So it gives you the flexibility to operate between them. So yeah, so that's, for example, one of the things that you wouldn't want to write yourself if you're writing your own linear algebra library. Okay, so another thing that Eigen can do is treat your matrices as geometric transformations. So if you include the header eigengeometry, it also lets you do a bunch of, say, rotations, 2D rotations, 3D rotations. So if you want more detail, you can again read the documentation, but it's just another good to have things if you're working with like matrices in graphics or yeah, anything sort of geometric related. Right, and on to the most important bit, which are solvers. So the most basic kind of solver, as I've mentioned at the start, is say I have a known matrix A and a known solution B, and I want to solve for the vector X. So this is a very basic kind of linear algebra operations that you need to do for lots of time evolution, for example. So here I have the most simple example of how you do it. Right, so I first built a matrix A and a vector B. Then this is a line where the operation happens. So what you need to do is you first do one of the decompositions that will help you basically factorize your matrix A so that you can solve it easily, this system. And then you give it the right-hand side B so that you can solve it. So typically, when you solve these linear equations, you would have two steps. You decompose it, and there are different sort of decompositions. And here I've just give you some examples. So LU and QR are very typical ones, and there are different pivoting, for example, that will give you different performances. So depending on the matrix A that you're looking at, say, depending on the size, whether it's symmetric, whether it's Hermitian, complex, real, you can use different decompositions to suit what you need. So different decompositions will have different accuracy and also different optimizations that has been implemented under the hood. So you should look at the documentation to choose the correct decomposition that you need. So once you've decomposed, you can actually reuse the decomposed form and then solve with various b's. Say I have ax equals b1, b2, b3, then I can reuse the decomposed result and solve to accelerate the next solving. So some other solvers that I've mentioned and might be useful depending on your application is singular values or eigenvalues and eigenvectors. Again, which one you should use depend on the matrix you're looking at, whether it's a complex matrix or a self-adjoint. They have different properties and speed, very crucially. And also, Eigen has solvers for sparse matrices, but I would say that some other libraries like PETSI, they have much more sophisticated solvers if you want to look at sparse matrices. But these will probably be good enough if your application fits onto, say, one node. Right, so the solvers I mentioned before are direct solvers. Now, if you have a system where it's very large and very sparse, very often it's more feasible to use an iterative solver. So basically, rather than solving for the inverse of A, you try to approximate your solution X to be closer and closer, and you try to minimize the error by continuously multiplying by A rather than finding the inverse. So yeah, sometimes this is the only thing that you can do when it comes to big systems. And methods like conjugate gradient and big step, these are very established methods of iteratively solving these sparse systems. And very often you'll use with a preconditioner to make sure that you get the accuracy and also that your problem will be well behaved and doesn't lead to very big instabilities. So before we look at the demo, just a few general notes about using Eigen. So when you're testing it, normally Eigen does a lot of checks behind the scene to make sure, say, your types are correct. But then in production, they can slow down your calculations. So I would recommend turning optimizations on and turning off debug. So you just have to activate the macro and debug to make sure it doesn't do all the checking behind the scene to slow down your calculations. And also, as I mentioned, there are lots of libraries, some open ones, some vendor provided ones that have some optimized linear algebra routines that you can use. So if you use Eigen, you can enable the macro Eigen use BLAST or Eigen use LAPACK to use these optimized libraries that you have been provided with. So yeah, so you don't need to use them, but then if you have one, it could accelerate some of your routines, like your gem or your decomposition could be optimized by the vendor as well. Okay, so do you have any questions? And if not, I think I will go to the demo now and go through some of the methods that we've discussed in the previous slides. Okay, so the problem that we'll be solving together is this diffusion equation in one dimension. So here, this is the equation. So yes, just as if you're familiar with it, what this is describing is that T is a say could be concentration, could be temperature. This field, as it evolves in time, it would depend on the neighboring values with this second order differential operator. So basically, if you imagine if your neighbors are higher, you will flow to somewhere with a lower value, and this is exactly what diffusion is. So how we solve it with the explicit method is, say we have a field at time n. So this subscript is the time, and we try to iterate to the next time step. So we go from n to n plus 1 by multiplying a matrix. So this matrix will represent the differential operator, and this is just discretizing through time. So yeah, I'll just repeat that again. So we have the initial Tn. So at time n, I have the field, and then I have a matrix that I multiply to get to the next time step. So if I want to simulate time evolution, I'll just continuously multiply by A successively. So I have the code in the exercise folder. So you can have a look at it later on, but I'll go through them together. So, okay, so this is the same diffusion equation as before, just that I've discretized it. So now the difference between the points is finite. And so you can see that for the next time step, n plus 1, the value at a certain point depends on its neighboring points. So I minus 1 and I plus 1. So what's in the bracket, it's the position, and the subscript is time. So yeah, again, the value in the next time step depends on its neighboring value. So as a matrix, I can write it in this equation where A is this matrix. So as you can see, on the diagonal, it's close to unity, and this delta just basically mixes your neighboring points to represent the differential operator. So okay, so maybe I'll show my code editor so we can look at how we build this together. Here. Right, so do you see my editor? So yeah, the code is on the GitHub repository where all your exercises are. And if you pull that into Archer, then there's also a makefile that you can make it straight away. So, okay. So as I mentioned in the slide, you would first want to construct your matrix A. Actually, maybe I'll share the entire screen so we can have it side by side. Okay, we can have side by side. So right, so sorry. First of all, we want to set up the matrix A. This is matrix A. So how do we do it? So one of the methods I described before is I can first allocate the vector. So with n square elements, because there are n squared elements in the matrix, so I applied the map to view it as a matrix, dynamically sized matrix. So as you can see here now, I have a matrix A that is the right size. Now to fill this matrix, I would just have a loop going through all the individual elements here one by one. So you can see I'm just setting it to right. So first of all, I just put the identity matrix, which gives us 1 in the diagonal, and then I just add and subtract the deltas as appropriate. Right, so if I make this, and I run this, so okay, it will print out what A is. So this is the matrix, which is just like what we have here. So I've set a value for delta. So I've set up my matrix A. Right, the next thing I want to do is set up my Tn, which is the initial condition. So I just set it up as a step function. So I put a vector where the first half of the values is 1 and the rest is 0. So if you can imagine, what this will do is it will smooth out the step and just flow to a uniform temperature, say. Right, so for each step now, as I loop through, I want to multiply by A. So what I do is, in a loop with a set number of steps, I will multiply by A. So every iteration, I'll multiply by A once. So let's see what the result is. So when I run, I've just stored my results here. So if I just show you what's in here, right, so you start from a step function with just ones and then zeros. You can see it starts to smooth out the values. And I've actually written a Python script that will show you what this is. So it will just load this file and show you what we have solved. Okay, so you can see that initially, yes, right. So as you can see, it starts with a step function and then it smooths out. It's very simple. For every time step, it smooths out a little bit more. So is the statement b equals a times b smart enough to not allocate new memory for b? Yeah, so it won't allocate new memory. It just reuses the memory. You're overwriting the old b. Cool. Yeah, I guess, well, for what I've done, I've just written out b in a separate file, but internally, cool. Okay, so this is the most this is the most basic example that we can do for any sort of simulation using matrices. No module. Oh, okay. So if you're running this on Archer, I don't think this will work because it will depend on matplotlib, and I think you need to forward your terminal in order to see the results anyway. So yeah, if you want to visualize the result, I'm not sure you can do it on ARCHER2, or at least easily, but you can do it locally though. Yeah, that's why I'm running this not on Archer. I'm just running this locally. But you can still look at the results. The whole file of explicit sim. Yeah. If you want to just write a script to visualize all these results, you can do it. But yeah. Okay. Let's go back to the slides. But yeah, any other questions? If not, okay, let's try to use the implicit method now. Yeah, so this is just the code. I've pasted that onto the slides. But okay, so let's try to solve it with the implicit method. So previously, you can see that for each step, the left-hand side is a new time step. I multiply the evolution operator to get the new time step. But what the implicit method is that I'm trying to solve for the new time step now. So you can see that this a is a different a, but it's on the left-hand side. So I need to solve tn plus 1 basically by inversing a. So a benefit of this is that it actually, the implicit method, even though it seems a bit more complicated, it actually gives more stability in terms of the algorithm. So actually, depending on the size of delta here, which is how much we mix with the neighboring points, and also how fine our time steps is. So you can see there's a trade-off. So if I have very fine distribution to get the same delta, I will need to decrease my time resolution as well. I'll have to make my time steps smaller to get the same delta. So one problem is that with the explicit method, if your delta gets too large, this method actually isn't stable. You will get the wrong result because your time step is too big, or your spatial resolution is too fine. So what you need to do is the implicit method. So this is actually much more stable. I think for this particular example, it's stable for any value of delta. But you can read a bit more about the comparison between the methods here. But yeah, so as you can see, rather than just multiplying by a, this time I need to solve for tn plus 1 now. So this delta is this a is slightly different from before, but you can see this, basically the sign of delta is just flipped. So this is minus delta, delta, this is plus delta, minus delta. So, right, let's look at the code again. Yes. Okay, now look at implicit. So what we have here is very similar. So I again constructed the matrix A, slightly different. Previously I have minus, and here we have pluses, but you can see that I can print the matrix A out here again. So this is a matrix A, which is of the form of this matrix A. So, yep, just to show you that we've constructed our A correctly, and we set up the same initial condition. So we have the step function again, but what's different is this part. So rather than just multiplying it, what I do is, just like the example I've given in the slides, you first decompose it, and then you solve it. And just like before, you don't allocate new memory for B, we just reuse B again. But then you have your householder QR, and then your solve. So just to show you that this method also works, now I've written it to this implicit sim. Let me just show this instead. Right, so you can see it basically has the same behavior as you would expect, because we're just representing the same physical problem that we have in a different way. So the solutions had better be similar, if not the same. So yeah, any questions about the implicit method and solving with the decomposition so far? If not, then I will show you what the exercise will be. And yeah, so basically in this explicit method, we have constructed everything with dense matrices. So you can see that this matrix is constructed as a dense matrix. So if you look at back, this is our A. There are lots of zeros here, so it doesn't really make sense for us to sort of save it as a dense matrix, especially if our system gets bigger, there will be even more zeros. So let's try and do exactly the same operation and see what we get. So in the file sparse.cpp, you can get the solution, but I would encourage you to try and modify your explicit.cpp to use sparse matrices to see whether you can get it to work. So I've given you some hints here to help you get started, and you can just fill in and change some of the functions. And I think I'll give you, say, 15 minutes. So maybe at 2:05, we can have a look together at the solution and see whether it works. And in the meantime, you can write on the chat if you have any questions. So yeah, in 15 minutes, I'll go through the solution, and then we will take a break after that. Right. Okay, so it's 5 past. I hope you've all had a chance to attempt the implementation with sparse matrices. So I'll just very quickly go through. Before I go through it, if you have any questions, feel free to pop them in the chat. Otherwise, I'll just go through how you would implement it and some of the points, and then it will be a break. So, okay, let me just open it up. So basically, compared to the sparse dense matrix implementation, so the first thing that you need to do is to include the sparse header and then declare a sparse matrix instead. And then what you can see here is you declare a vector of triplets, and then you fill this vector with the triplets exactly the same as defined in the explicit one. So you can see for each element, you give the coordinate and then the value. And then what you would do here is just have the coordinate and then the value So you can see that actually the implementation here that I have is a direct translation as before. So exactly, so I see from the chat someone pointed out that you reserve 4n rather than 3n. Yeah, and precisely because I want to have a direct translation, but you can also do it with 3n as well. But one thing that you notice is, as I've set it up here, there will be duplicate elements. So for example, the I here will be the same as the I plus 1 from the previous iteration. So when you do this set from triplet, if you have duplicate elements, what it does is that it will sum them up instead. So if you have multiple elements specified for, or multiple values specified for one element, then what it will do is sum up those elements. So it just helps, in certain cases, help you simplify your pushing back process. So, yep, so you can see set from triplets, like I've mentioned in the lecture, and then, yep, the rest is just the same. So the actual calculation is just like the explicit case. You just multiply them as you would. So just to show you that it works, let me run it. Right, and then if we do the same simulation thing again, let me share that. Share my entire screen. Yep, so this time is saved in sparse sim. Right. Right, so you can see it does exactly the same thing as it did in the explicit case. So that's all good. So yeah, so now I'm hope you're all comfortable with using eigen and how it manipulates different vectors and matrices, and understand that using the solvers isn't very complicated. And if, again, if you want to use some optimized versions of it, you can enable the macro to give you more performance for certain hardwares. So yeah, do you have any questions? If not, then I believe it's your break, and we'll come back at 3 for your next session about threads.
Okay, so it's 3 p.m., so we can continue with the last lesson of this course. I will share my screen. Give me a moment. Before I continue, I'd like to ask if there are any questions or anything that you would like to If not, I will continue. Yes, please, if you have any questions, or please let me know in the chat. So in this part of the course, we will learn a little bit more about C++ threads. So we will see introduction, how to create and joining threads. You will understand better later what join means in this context. Passing arguments to threads, and synchronization. So what we will see today are C++ threads. That this way of handling threads is available since the C++ 11 standard. Is a similar functionality to POSIX threads, but in this case we have a proper object-oriented interface. These threads are portable, so are available in most compilers today. And when we to create a thread, we create at the moment that we create an object thread, the thread is created. It's not. It's slightly different that when we're using POSIX threads. Well, actually, POSIX threads we don't handle objects, and we will see how to synchronize, how to do synchronization between threads. That we will see three different. We have a mutex logs, condition variables, and C++ atomics, and also we will have a task. We will see later how we can handle this task in order to do things in a asynchronous way. So to create a thread threads are objects of the standard thread class, and these are created when we call the constructor of this class. When we call the constructor, we will need to set the function that the thread will execute. In this point, this is similar with the POSIX threads. Also, well, we can share the function pointer, or we can also use a lambda expression or function object. Here there is a note that is you cannot copy a thread. A thread, this is kind of a function that you execute in parallel, so making a copy of a thread doesn't make that much sense. So that's why here is said that, well, it's not possible. When we talk about join, actually it's a rather wait for the thread to finish, because we create the thread and we tell the thread, okay, do this operation, but we will need to wait before finishing the execution. We will need to wait for the thread to finish the task that has been assigned previously. Here we have a hello world with using a function pointer. So you see that well, we have the here we are using the library thread iStream to print a message in the standard output, and the library vector. So you see that we have this function here. This is also this function. The structure normally returns void. I mean, means that you don't return anything. And here what you are doing is you are just printing on the standard output hello for thread, and you can get this thread get ID. You get the ID of the thread. That is kind of a random number. It's not doesn't follow any. So we have here the main function. We have the vector of threads, and here we have a standard. Well, yeah, can call it a standard or like a for. And what I'm doing here with the threads pushback, I'm adding object threads to this vector. And what I'm doing is I'm creating the thread in a standard thread, and here as an argument, I passed the name of the function that I want to execute. So here I define my vector. Here I execute 5 threads, creating them. Now what I'm doing here before finishing the execution, because at the moment that we reach the end of the execution, the program finishes and the threads also finish. So we could we could finish the program before the threads has been executed. So what we have here now with another type of for loop, more using an iterator, we have a thread join thread join means that I wait until the thread has finished. That's why we save all the threads in a vector. This is another way using a lambda function that is similar, but what I'm doing here, I'm specifying the function inside rather than defining it here. Personally, I see that this is like a little bit more, well, okay, here because we only have a line could make sense, but I don't know, I find this like more readable than this. And also in the moment that, for instance, you have a lot of lines, that could be a little bit, but well, this is just to let you know that you can also use a lambda function. Also thread IDs, in a thread you can call get ID using a standard this thread get ID to call it an executing thread, and returns an arbitrary identifier. Doesn't have that much use. Maybe for debugger purposes you can print it, but if in case that you want to number threads in a sequentially, you will need to pass the number as an argument to the thread constructor. Okay, to pass arguments to threads, it's pretty similar. Well, pretty similar is we have this function, that this function will be executed by the thread. You have a function hello with these two parameters, and you print hello and the numbers x and y. So here in the main, you define two numbers and you create a thread. My thread, and in the constructor you specify hello, that is the name of the function, and a and b, that are the parameters that we will send. You will send, and then you wait here with my thread join, and once that this thread has finished, or this function has been executed, you finish the. Here, when we use int x, int y, we pass these arguments by value. If you want to pass a reference instead, because you want to modify x in the, or for instance, imagine that you want to open a file or do an operation or connect to a database, and you do a calculation and you get this x here. So you can do, what you do is you send a reference to x, and in that case you can modify x. So this is to pass by reference. At the beginning x is 9, but when you finish, you print x is 10 here, because you have executed this. Okay, so this is regarding how to create a thread and wait until the thread has finished. Now we will see how to synchronize, or how to, let's say, synchronize when you have several threads, not to create a race condition. What is a race condition? Is when the several threads try to modify the same value in memory of the same variable. So here we have a class wallet, and here we have money. So it's the integer, because well, imagine that you have a £1 coins, and it's what you want to, so you don't have a floating point numbers here. You have the default constructor, and also you have this function here that is add money. So what you are doing is you pass by value this the money that you want to add, and the variable money is updated, m money. But the problem is if you execute this using several threads, could be a race condition because you could get this value could be updated, and maybe you have read already this value, and you so imagine that you have 0 and you want to add 20 and 30, the result should be 50. But if there is a race condition, could be made either 20 or either 30 because the thread could have taken this old value rather than. So here we will need a mechanism to synchronize these threads. And we'll say basic one, but this one is also available on the, if you use threads, sorry. If you use C and POSIX threads, is the mutex. So this is a log, and what you are doing here is you define the variable that you want, let's see, the share variable, and you define the mutex here. So when you execute add money, you log the mutex, you execute the operation, and then you unlock the mutex. So this is like I put the sample last time of a toilet, but yeah, I think that still works. That when you enter, you lock the door, and nobody can get into that into the. So and when you finish, you release you unlock and you leave the. So this is a pretty similar concept. If another thread arrives here and executes a mutex lock, and this has been already locked, wait here. Keeps waiting until mutex is unlocked. You need to remember every time, but this is kind of when you write a code, we say best practice. We learned before if we allocate some memory, we will need always to free the memory or make sure that the memory is freed at some point. You will need also to unlock because otherwise, if you execute several threads and you don't execute that, the rest of the threads will be here in a locked state. To avoid, or there is another way if you don't want to use mutexes and you don't want to like lock and lock, you can use the lock guard is called. So this class implements what we learned before, the resource allocation is initialization pattern for mutexes. So what it does is at the moment that you finish the function or the thread finish, unlock automatically so you don't need to call it explicitly to. So this is the sample here. So you see here that you define the same, you define the mutex, but here you call a lock guard with the same variable mutex. So you execute that, and you have a mutex unlocked when lock guard goes out of scope. So at the moment that you finish the function, the mutex is released. This is helpful when you have this function that is like, let's say they do an atomic operation. But in the case that, for instance, you want to include here more operations, maybe this is not the right, so maybe the mutex is needed. But yeah, this is just to show you that you can use, well, mutex would be used, but you can use in an explicit way, or you can use a lock guard in order to unlock the mutex when the thread finish of this variable goes out of scope. This one. Atomics. This is this makes sense when we are working in the previous example, we're working with this variable, so just one. So in that case, this is an atomic operation that you are doing here, and in order to save, let's say, effort in writing creating a variable called mutex, log, unlog, etc., you can create an atomic variable, it's called, where you do atomic operations. In this example, we are using integers, but a floating point support is available from C++ 20. So the way of using that is quite, actually, I would say quite elegant, in the sense that you just you're using an integer, so you declare a standard atomic, initialize to 0, and when you call the function, you just update the value, because this variable behind the scenes, they have the log, unlog, etc., but you don't need to worry about that. Is there a, I think maybe because I'm like a, I will try to, because I'm talking and I'm moving like my head between screens. So, okay, maybe something, yeah, I see that in the chat that there is something wrong with the audio. So maybe, okay, if maybe something with the internet connection that sometimes could be a little bit, yeah. Okay, so I will keep explaining, and please, if you have any questions, please feel free to ask them. Okay, so this is to update money using an atomic increment. To use a mutex, for instance, is when we want to do more operations inside this log and unlock. Might make sense, yeah, could be sensible to use an atomics. Here, what is explained is that to lock and unlock the variable takes some time, or to use atomic is not the same as using an int. It will take some time of locking and unlocking. So be sensible in the sense of don't overuse muteces, or don't use a muteces if you don't need to. I remember in the past I was writing an application using POSIX threads, and we detected that using I think was from 8, we were using 8 threads and 16 threads, and the performance was pretty similar. It was not an improvement. And using a profiler and checking what was going on is because we were using a mutex to update a vector, and actually this mutex was not needed. So we removed that, and the performance increased a lot. So be careful with the, I mean, if you needed to use one of them, use it, of course, because they're available. But if you can avoid it, also, yeah, go ahead and do. Any questions so far regarding this part? Also, we have here a note of this, the license. If not, I will continue with the second part of threads. So we have further topics, and what we will see here is how to use async and futures, parallel STL, and also, well, comparison. Some thoughts, I would say, about C++ threads or OpenMP, because you may wonder, why do I need to know C++ threads if OpenMP exists, or they were around? Why do I bother to use OpenMP if I can use 3 C++ threads? You may have noticed that when we use a thread, there is no direct way to get a return value from the function lambda that the thread executes. You can get a reference, an output reference argument, but yeah, could be in some cases could be a bit problematic. But one way to get around this is with the std async features. The idea of this is similar to the threads, but the thing is when you call it, you get a variable that is updated when this task is finished. Another advantage of this is that you can handle they can throw an exception in case that the thread throws one. And this is what I said, async returns a future object. Future in this case is like a double meaning. Future is like also the class of the object that returns. And we would need before we were using join to finish the thread finish, and here what we would call is a get in order to, because this future object could be initialized or not. We would need to execute get to make sure that the future object contains a sensible value, doesn't contain nothing wrong or nothing that has not been calculated. So this is the way of using async is we have our function here. You may notice that rather than using void, rather than using that not returning anything, here we return an int, an addition of x and y. And here we have my the body of the program, main, AB, and what they create here is I create a future object that is an integer and is called FUT. And then here I execute std async. So I use the function name add, and then A and B, that are the arguments of the function. And what I'm doing here is I print the value, but if you see I execute future get, because maybe when I execute this, I don't have a, let's say, guarantee that this will execute it at the same moment that I call the function. So I need this is kind of a join, or kind of okay, do this, and then you get the result. This is a way you can also use if you want to save writing this, you can use auto. Well, problems, things that, but this is what they said, when you created this task, doesn't mean that you will execute the task at the moment that this is called. This is kind of like a launch on, the thing is, I think it's the, I'm not sure if program was operating system, the one that could decide, okay, let's execute it or let's not. So it's a little bit of out of control. And the thread, in case that is like a, let's say, a heavy operation, it will be executed at the moment that this is when the foot get is called. That's why it's like async is asynchronous. Also, you can force the execution to like execute it at the moment. If you do std launch async, you force to these tags to be executed let's say, faster. And also, there is like you don't have that much control. This not because this is here we are talking more about the task rather than thread. You execute the task, but maybe you execute 20 of them, but doesn't mean that you will create 20 threads. It's like you will execute 20 tasks in parallel. So to create a thread, let's see that there is not that much control with that way of doing that. Second part is parallel STL. Here, this is not updated. They said that it's not yet available in most standard library implementations, but actually is available in most of them. And this is part of the C++ 17 standard. And the STL algorithms that the thing is, for instance, for sorting, you can do it in 4 different ways. You can do it in sequential, fine. You can do it in parallel. You can do it in parallel and vectorize. Vectorize means that sometimes, the processors, the cores, the arithmetic unit and the floating point unit could contain called vector operations. That means, for instance, if you do an addition, you can add 4 numbers in one instruction. When I say instruction, means instruction at processor level, assembly level, like a machine code. This is if you use a vectorized operation, and that means that in one cycle you will execute 4 additions rather than only 1. This is what I mean with the vectorize. And also, well, from C++ 20, you can do it vectorize, but not in parallel. Here I have an example with have a vector of integers, and I get I can sort the vector, and I can get I can do the sequential sort. I can specify that I want explicitly to do it in a sequential way. I can say that I want it in a parallel execution, and also I can say that I want to allow the vectorization as well here. The issues that I may find with this is that you tell the library to do it in parallel, and sometimes it, well, yeah, would work and we will get this done faster, fine, but we don't have control over how many threads we use, how the threads are handled, if that is like a static dynamic assignment. It's like a little bit out of control for the programmer. This is like we rely on the library. Also, here is mentioned that we don't have that much control to control the data affinity or locality, because again, this is like done by the library, not by us. So maybe in some machines it's very efficient, but maybe we use other machines and it's not that efficient. But yeah, this I guess that this in future iterations of the C++ standard will be better. Okay, here what I said, there are some thoughts about C++ threads and OpenMP. The thing is what I see is that the standard goes faster than the implementation on OpenMP. What I mean with that, for instance, OpenMP, the version 4.5, only supports C++ 98. That actually this is like more the C++ that I used back in the time when I was doing my degree. OpenMP 5.0 supports most of C++ 11, 14, but you know that there is now 17, 20, 23. So that is like because one thing is the standard is released, but you need to wait for the compilers to use the standard, and also you need to, in case that you want to use OpenMP, maybe you cannot use the latest of features of C++. Sorry, yeah, C++. Yeah, it takes like some years in practice, but yeah. Oops, sorry. The other way around is also OpenMP. We have some useful features that are not available in the C++ standard. We have a thread barriers. That these thread barriers means if you use OpenMP, if you use MPI, you can have a barrier. So when all processes reach that barrier, it keeps or let's say it's like a kind of a synchronization point for all the processes. And for threads, we can do that with OpenMP, but with the C++ it's a little bit more, it's not possible or trickier, I would say. Thread pools and task is something that is available on OpenMP and not on task. This is not here, but also a recommendation that we use OpenMP, you should be careful on the number of tasks that you are generating. Could be the case that you generate a lot of tasks and handling the task list, let's say, it will take more time than doing these tasks in a sequential way. In these cases that we may have it depends also on the granularity of the task that we should consider. If the operation is quite simple, maybe it makes sense to create several or to perform several operations using a task rather than creating tiny tasks. Parallel for loops. Okay, that is in parallel str, that is std for each, but yeah, since that OpenMP is maybe more convenient for that. SIMD directives, that is like a single instruction, multiple digit vectorization directives. Here, the idea is that these features could be implemented using C++, but could be a little bit nightmare in terms that you will need to write a lot of lines of code to perform an easy operation that could be done using OpenMP. So here, the point of this part is not to say that C++ threads are the best or OpenMP is the best. So you should know both ways and choose according to the best performance or according also to the time that you have to parallelize a piece of code, what is best for you. In some cases, it will be more convenient to use a C++ threads. In other cases, with a pragma in OpenMP, would be good enough. The same with the STL libraries. If you perform this in parallel and the performance is good enough, that's it. Because sometimes maybe you can spend several weeks just to gain a few seconds. Okay, if these few seconds, if you're doing your programming a real-time application, means a lot. But if you are using a software that the simulation takes 6 hours, a few seconds in 6 hours doesn't make that much difference. So this is up to the programmer to see what is worth implementing or not. Also for GPUs, there is OpenMP, could offload code or offload a task to GPUs. This is like getting better. Here is mentioned that there are like there is a SQL, Cocos, Raya, that there are some C++ frameworks that implement that to some point. More differences between OpenMP and C++. Mentioned here there is some data members of objects in private or reduction clauses. The reduction is different in OpenMP and C++. OpenMP, you don't have this forking joining of threads. Normally what you is you write a pragma and you have kind of a barrier that you wait all of the threads to finish. C++, there is no standard way of binding threads to sockets and cores. What means binding is you have for instance, on ARCHER2, you have two processors of 64 cores each. And when we do, let's say that you execute a software that use, let's say 64 threads. So you can say the thread number 1, that this is a number that I assign. The thread number 1 will be executing the core number 1, the thread number 2 in the core number 2, etc. Also, you can leave some, so maybe the thread number 1 will be executing the core number 1, the thread number 2 will be in the number 3, etc. So you can do a distribution, you can do some binding of threads to cores. This is important because ARCHER2, one node of ARCHER2 is NUMA. NUMA means non-uniform memory access. So let's say that core number 1 could access a part of memory very fast, but other parts of memory, because there are like in this motherboard physically are farther away, would take more time to get them. So in that case, binding is important because if a thread is bound to a core, all of the is a way also to make sure that this thread access the fast memory rather than access part of memory that could be slower. I know that I think this is possible. I remember to bind threads to cores using the POSIX threads, but it seems that with C++ is not that possible. However. And this is also another example where you can do this in OpenMP or not. I mean, if you are parallelizing a for loop, I will not bother. I will use OpenMP. But could be the case that you want to use threads. For instance, here I have like the execution line or the timeline, let's say. So I'm executing my code. I need 4 threads. So I created 4 threads. So let's say that this is a loop. Fine. I execute the loop in 4 threads. And then here I have this thread barrier or finish of the for loop, pragma, whatever you want to call it, and you continue with execution. You can also do this in OpenMP. Here you execute your software. I need 4 threads. Good. Now I need 2 more. Okay, now I finish. And then, so see that there is like some regularity or some, but there could be the case also. Normally it happens with the search algorithms that the algorithm could be irregular. What that means that you don't know beforehand the workload of a region. For instance, you have this happens with the optimization in terms of mathematics optimization problems, that you are searching the global minimum or global maximum, and you can have some regions that are easily you can discard them because you know that they don't contain a solution for our problem, and maybe you can discard 50% of the search area in just one iteration. But the other 50%, it will entail much more work, and you keep dividing, you keep, and it will generate much more work. So in these cases, for instance, threads will be a possibility. When I talking that I used in the past threads was to do that, to go through a search tree and handling the workload, because some regions they were more let's say expensive, or they were like a lot of operations involved rather than other regions. And this is for instance, if we have this pattern, this cannot be done with OpenMP. Well, if we use OpenMP task, maybe, but here, for instance, we have an operation, but this operation executed 2 threads. This operation, this first one finish, so these 2 threads execute. This one maybe create this. That's also the thing, that the one thread can create other threads, and also you can have a look or have keep account of how many threads are launched or executed in parallel. So it gives you like a more flexibility. Okay, see that there is a question in the chat that they say, can't we solve this problem with the dynamic scheduling, the regular workload? Yes, of course. Yeah, that's the thing that exactly. When we have, if we have a regular workload that we know beforehand what will happen, what we do is we can do what is called static scheduling. So you have a region, and you have 4 MPI processes or 4 threads, and you say, okay, this part of the region, you divide the region in 4. This part is done by the thread 1, this part by the thread 2, and so on. When we have a regular workload, we will need to use a dynamic scheduling. So we can do, for instance, we can at the beginning, just to let's say to start the execution, you can divide the region into 4. But imagine that one region is discard and is solved. So what you can do is, but yeah, this is like a dynamic scheduling, that the threads are doing work, and one thread detects, oh, there are 3 threads working rather than 4, and they can create a new thread, and you will have again 4 threads. And when you create this thread, the workload of that thread could be divided into 2. Not sure if that makes sense, or I like talking no sense, or if this is clear, or I like going a little bit out of topic with this. Okay, so yeah, this is the end of the presentation. we have, if we go here to this website, I will make this a bit bigger. We have practical exercises. We have an exercise here of a simple use of threads. Well, we have here the OR URL that still works, but you can use and the thread is, if we go to exercise and threads, you have area CPP contains a C++ version of the Mandelbrot example, and you can parallelize the outer loop of the main computation using C++ threads. You can use a function pointer or a lambda expression, try different mechanisms, mutex, locguard, and also you can use an atomic int. So if we go here to the repository view, you will find here exercises, threads. So here you will find this, well, the instructions and the code that we are talking. So this is the, do you have any questions of regarding of threads or regarding anything of what we have seen of during this course? There are questions about C++. If not, there are 10 minutes until the end of the course, so you can stay here and ask. Yes, the solution of the exercises are, if you go to the main repository, this is the main repository, you can go to there is a branch that is called solutions, that this branch contains some solutions. This is still like a work in progress that we want to make the solutions more visible. But if you go here, you will find that these exercises have been, like these files have been solved. So here you can find the solutions. Also, in case that for some reason a solution is missing or something is wrong with you can always submit an issue here. For instance, there is an issue here of a missing link. And also you can submit an issue saying that the solution of this exercise is missing or this part is not, so we can improve the lesson. There is a question in the chat if we will talk about Cocos, if there is a lesson here, but this is not covered in this course. We have a lesson here about, I think here talks about Cocos or Raja, but yeah, we are not, you can have a look at this lesson, but yeah, this is not covered in this course. I wonder if there are exercises. Ah, yeah, there is an exercise here. Well, here they explain using Cirrus, but yeah, this is afraid that this, yeah, this is not covering the. Yeah, I think it's yeah, this is it's possible to use it on ARCHER2. The thing is, yeah, feel free to try. Also, in case that there are some, the thing is, I'm not sure if because here in the, let me check. Okay, the issue here that Cocos is used with the GPUs, and ARCHER2 doesn't have GPUs. So that's why here is mentioned that you can use it on Cirrus, and the modules that you load is a GCC, CUDA, that is not in ARCHER2 because there are no GPUs. Well, and Cocos is installing on Cirrus. But I think that Cocos also could run in the. Yeah, to be honest, I'm not that familiar with this framework, so I cannot. I think this is done in GPUs, but yeah, no. Login zero, which what did you use to login zero? To do an SSH connection to ARCHER2, you need to use login.archer2.ac.uk. Not sure if login zero, maybe that is this is a typo that is in the. Yeah, I mean that's the thing that this is not. This exercise has not been updated. The thing is that this lesson in this run of this course we are not working with Cocos. The thing is we didn't delete that part in case that you want to use it for future work, but or for in your own time. But yeah, no. Actually, yeah, there is a typo here that is a notebook, not a notebook. Yeah, so I don't know what login zero. No, this is it. Okay, I see login zero, but of Cirrus. Cirrus is another HPC machine, it's not ARCHER2 that contains GPUs. Because I think that this part of the course was run on Cirrus rather than on ARCHER2. That's why we are not delivering this on. We will make a note in the repository saying that this is like other exercises that. No problem. So okay, this is the end of this course. You may receive tomorrow or next week. I will say, yeah, tomorrow of next week. an email with with the feedback form. This is important. Please fill in the feedback form. Is quite short. If you go here, you go training, upcoming training. This is the course that we are running. Also, these are the recordings of the first sessions. I think by the next week it will be the rest of them. And here you have the feedback. This is the course that you attended, and the only mandatory question is this one. So how would you rate this course? And the rest of the questions are optional. But yeah, for us it's important to know what we have done well, and to know what we can improve for future runs of the course. Also, if you need a certificate of attendance, you can reply to that email asking that. And also, if you have any questions or anything, or you want to keep in touch, please do so by replying to that email. I hope that the course has been useful. It's a little bit like difficult to, let's say, to cover everything, and also to have like a different audiences of people that come from Python, from C, from Fortran. But yeah, we hope that the course has been good enough. Yeah, looking forward to having you in more courses. And yeah, please, if you have any feedback, we will be happy to. I see there is a question. Can you suggest some resources for developing C++ code for HPC? Okay, that's a good question. That I would say to develop for HPC, you will need to work like a program in parallel. So my suggestion is here. Normally we have some self-service courses that is with using MPI and OpenMP. Here the samples, the exercises that we have are either using Fortran or C++. So if you do one of these courses of OpenMP and MPI, you will have exercises in both programming languages. Or I will say that most of the courses that cover OpenMP or MPI, they will tell you if the exercises are in Fortran or in C or C++. Also here you go at the past courses and material, you will find the past courses that we have run. Okay, so thanks once again, and hopefully you have a nice rest of the day, week. Yeah, bye for now.